All right. So we're going from Unit 1 to as far as we get to today. So we have 2 days. We have this Friday and then, not next Friday obviously, but then the third Friday to get through the whole year. Okay? So where are we going to start? What do we learn first? Conversions. What about conversions?
God bless you.
What else am I going to put up here?
Vectors.
I'm still under conversions.
Oh, sorry.
Okay.
Changing
Subscripts of 10. How do you do
Powers of 10. You need scientific notation.
Exactly.
So you'd be able to go from meters to kilometers to micrometers to decameters. Okay, you need to know all your conversions. Remember, you have to do, if this is meters, meters go on the bottom and cancel out, and wherever you're going goes on top. Okay, if you're ever struggling with your units, just do it that way and it's going to get you through every time. What else did we learn besides conversions?
Vectors.
Vectors, what about vectors?
They add to the
Good. Tip. Tail. Okay, what else?
Use the magnitude to find resultant.
Good. So if I have triangle, I can use Pythagorean theorem, or how else would I find one of these other sides?
Sine angle.
Yeah, so trig.
Trigonometry.
So when you're doing your problems where you launch the ball at an angle, okay, you have to do your trig. Because it'll give you theta. You gotta draw your triangle, then find the x and y components. So being able to break it into components. So break into components, or to break it out of components. So to find resultant. Okay, and then vectors have a direction. Okay. And what else besides vectors?
Scalars.
Scalars. Okay, so we can do a list of vectors versus scalars. Okay, give me a vector. Velocity. What's the scalar component of that?
Speed.
Speed. Give me another vector.
Force.
Displacement. What's the scalar part of that? Distance. Give me another vector. Acceleration. And the scalar part of that? The magnitude of A. And then I heard Amir say force is a vector, the magnitude of F. Okay, what are some other scalars that we generally deal with? Okay, but you may not have a vector component though. What about energy? Energy is a scalar. What's related to energy that's also a scalar? That you guys always mess up?
Work.
Work. Okay, impulse. Well, momentum's a vector, so impulse would be a vector. So momentum is a vector. Impulse is a vector. Okay. Time. Which one's time? Scalar. Alright, I don't want that argument that time has a direction. It doesn't. It's just a scalar. Okay. I feel good about this list. Is there anything else you want up here?
Graphs.
Graphs. Okay, so here's my graphs. I have displacement versus time. How am I going to get to velocity versus time? I'm going to get between those.
Take the slope of the displacement.
Okay, slope to go from x to v, and the slope of that is going to look like that. Okay, how do I get from this to acceleration versus time? Assume. But how do I get between them? The slope. Okay, yes, it's a straight line, but it's the slope, and it ends up giving me a negative value. Right? That slope is negative. Okay, how do I get from velocity to position? How do I go back? Area, which area under the curve? So to go from position to velocity to acceleration, you take the slope between those. To go backwards, you can take the you take the area. Okay. What else? What else have we learned?
Motion.
Motion maps. Good. Okay. So if here's a motion map of something falling, the distance between dots, distance between consecutive dots is what? Okay. What's constant between the dots? John? It's a second, or it's a period of time. And then you can also have an axis that has distance. Okay, so in this time, in 1 second, it fell how many tick marks? It fell a lot more tick marks than before. So it's moving faster down here. Okay, that's the motion map of an object that's dropped. You should remember that from the energy lab we did with phones. What else? What's next? Kinematics. So I'm going to just lump together 1D and 2D motion. What are the equations?
V over distance over time.
V equals distance over time, and that's V bar. What's V bar?
Change.
Average. Not change in, that's delta. Okay. What else?
Everything on the back of it.
X equals x naught plus v naught t plus 1/2 at squared. V final squared equals v initial squared plus 2ad x minus x naught. Ooh, I'm blanking on this one. Who has a reference sheet? Okay, well, they're all on your reference sheet, which you will have on the exam. Okay, so then how do we use these? What's the first step before we have to determine what equation we use?
Givens.
Givens. And how would you decide how we write out our givens? How do we write out our givens? Yeah, we write a table. Okay, so if we do an XY table, there's 6 variables in each column. Okay, there's always 6 variables we care about. X, x naught, v, v naught, a, t. And you always write out all 6. Okay, you always write out all 6, and then you do y, y naught, v, v naught, a, t on the other column. Which variable is the same always for x and y? Time. Perfect. So time is always the same. Okay, so time is always the same. So if you find time in one column, it's the time in the next column. How many variables do you need in one column to solve for something?
4.
4. So you need 4 variables. And then how do you find which equation you're going to use after I found 4 variables? I have any 4 variables. What equation am I going to use to solve for that next variable? The one that has all 4 and are unknown. So you look at what we don't have / what we don't care about. And then you find the equation that's missing that. So if I gave you the first 4 and I was asked to solve for acceleration, what do we not need and not care about? Time. So we find the equation without time. Right? There's only one equation without each variable. So we got to find the one without it and use that one. Okay? And the types of questions that we're going to be asked about this. Okay, if you're in 2D, you're going to launch a ball up and at an angle. Okay? So if I give you an angle, theta here, the first thing you want to do is you want to break it down into the components. So here's your V naught. Okay, here's your theta. Here's your V naught x, or sorry, y. Your V naught x. Okay, and just like breaking down our vectors, you can use your Pythagorean theorem or your trig to find the unknown components. And then you plug them into this table, and you find everything. What is the acceleration in the x direction, always? 0. Acceleration in the y direction?
Whatever it is. Or 9.8.
9.8. Depending on the problem, it'll either be positive or negative. You guys can tell. If you're dropping something, it's usually going down, so it's usually negative. Okay? And then you also have the problem of the cliff. Okay? So in the cliff problem, if I give you a V naught, okay, it's launched horizontally at 5 meters per second. What is that variable? Is that your V naught?
No, it's V naught x.
It's your V naught x. I said it was launched horizontally. Okay, so then your V naught x equals 5. What's your V naught y?
0.
0. Okay, so you got to be able to understand that when they give you a horizontal velocity vector, okay, that means it's only in the x direction. And if you throw it only in the x direction, it's not moving up or down originally. Alright, so I'm going to shorten this so I have more board space. What about the problems where you throw it straight up and you ask for maximum height?
It's 0.
What's 0?
The y something. Something right. Something like
Okay, so if I ask for the maximum height, we know something about these variables. Okay, we know acceleration is 9.8 meters per second. We should know our initial velocity. What we don't know is our final y, and we don't know our final velocity. Or at least it's not given to us. What's our final velocity? 0. If I throw my eraser up in the air, it goes up, stops, and comes back down. Okay, if I wanted to draw the graphs for that, it goes up, comes back down. My velocity is positive, hits 0, and then is negative. Okay, so you can get there from your graphs as well as just kind of like throwing an object up in the air, realizing it's going to stop, and then accelerate downwards. Questions on max height, graphs, anything like that? There will be a problem. One of these 3 problems on there for sure. No questions? Yeah, round up.
So the acceleration is
Good question. So if I start here and I have a height of 0 or a y naught of 0, and then I have a final y of negative 10, okay, which direction is the negative direction, up or down? Down. So acceleration pulls you in what direction? Down. So the acceleration is positive or negative? Negative, because the acceleration pulls you in the negative direction. If I flipped this and I said that this was 10 and this was 0, for whatever reason we're measuring going down, now which way is the positive direction? The positive direction is down, so then if my acceleration pulls me down, my acceleration is? Positive. So it depends on the context of the problem. Okay, most of the time it's negative, but not every single time.
Oh, that's 5.
Yeah, that was a made-up number for the example. Okay. What else? We can move on from 2D motion. I think I'm going to erase some of this board. What else? Call it out.
Forces.
Forces. Good. So what about forces?
Newton's laws.
Newton's laws. Good.
No, wait.
So there's 3. All right. Give me one of them. Draw me.
An object in motion stays in motion unless it's active.
So I'm going to abbreviate. In motion stays in motion. And then at rest stays rest. And then unless unbalanced force. So this tells us a couple things. What does this tell us? Okay, why does an object stay in motion or stay at rest? Kimberly. Inertia. So this is often referred to as the law of inertia. What else does it tell us? I'm specifically asking about the unbalanced force part. Okay, if I have unbalanced forces, what do I have? Acceleration. Okay, so unbalanced forces means there's an acceleration. But if I have balanced forces, what's my acceleration? 0. Good. Okay, let's try Newton's second law. Or third. Joshua. F equals m times a. And be a little more specific. It's F net. Okay, the net force is the mass times the acceleration. You can then break that equation up, and I can say F sub g equals m a sub g. F sub c equals m a sub c. Okay, so there's lots of different forces I can solve for with their specific acceleration components. Okay, but the only way to solve for F net using this is if you use the net acceleration. Third one.
Everything has equal and opposite, right?
Equal and opposite reaction force. Good. So what kind of problems do they ask about Newton's third law?
Kick a soccer ball. You don't hit a ball with that.
Okay, so you hit something. I kick a soccer ball. I punch a wall. I jump off the ground. Okay, the key words there are I kick something or I put a force on something. What's the force on me?
The same
Okay,
thing.
the same thing. It's always foot on ball, and then what's ball on foot? Floor on foot, what's foot on floor? It always goes back and forth. There's always that relationship in those types of problems. So just by that pattern, you should know, okay, Newton's third law, that's what you should think of. And you should be, oh, it's the same. It always is. If my bat hits my ball hits my bat. Okay, what else in forces?
Free body diagram.
Free body diagrams. So F, B, D. Okay, so you want to draw usually a dot or whatever your object is, a square. So you draw your objects. And then from one point, you include all the forces acting on that. And in the case of the ramp problem, we have to do another step. We want to break up the components so they're either in the x direction or the y direction. So then we want to break up vector components. So let's quickly do a ramp problem. There's my box. And now I'm going to draw my free body diagram. Give me a force on this box. Victor. Normal. Okay, the normal is perpendicular to the surface. Okay, so F, N. Joshua. Friction. Okay, if there's friction in the problem, yes. If it's frictionless, it wouldn't exist. But let's assume there's friction. What direction does that go? It opposes motion. So my block's sliding down the ramp. So let's say friction goes up the ramp. All right, Rosemary, did you have one? Gravity. Okay, what direction does gravity go? Straight down. Okay. And then, is there any other force? Aranda? Force applied, that's only if we're pushing it. And we usually don't push the block problems. But good, if the block's straight on the ground, or if we're pushing it up, right, you might have a ramp problem where you're pushing up the block, then we'd have an applied. Well, let's just assume it's sliding down because it's a little bit simpler. All right, so now, which vector are we going to break up into components? The gravity. We want to break up the force of gravity. So remember, you have to draw your axes. Okay, our x and y axes are no longer the normal x and y that we do every day. Okay, we tilt them so that it looks something like this. Here's our x, and here's our y. So we want to break up the force of gravity and put them in that x and y direction. So what's my first step into breaking up the force of gravity? Where's Melody? We make a triangle. So I want to draw from one of these two vectors. Is it normal or friction? Normal. So I always start by making a dotted line in the same direction as normal. And this dotted line is in the same direction as y. So if I break up the force of gravity, what components is it going to be? The force of gravity in the y direction. F, G, y. So then now how do I draw F, G, X? Okay, from the bottom. So do I connect it from the tip of FG down to wherever I drew my line?
No, it's pushing down.
No, I gotta go straight in the X direction. The X direction is slanted. So it's gonna look something like that. I then can fill in my F sub G line because now I know exactly how far it goes. And this is FG what? X. So where's my right triangle? Right there? Between what two vectors? FGY and FGX, right here. Which is what it should be, because between Y and X, there's always a right triangle. Okay. So now we can break it up and do the net force. We can add the forces together. We can solve for Fg and use our angles to then solve for Fgx and Fgy. If theta here is my angle, do I put theta at the top or theta right there? Which one? At the top. I always put theta at the top. Good. So then if I'm solving for Fgx, which trig function do I want to use? Sine. Okay, it's different than when you're solving for x when it's a normal plane. Okay? Because here, sine is opposite over the hypotenuse, so it's going to be Fgx over Fg. It's easy to memorize the fact that x goes with cosine, because 90% of the time when we're doing problems, it does. We got to think back to the original definition of sine, which is always opposite over hypotenuse. Okay, I think I got time. So let's continue on with this. There's two ways to solve for F net. What are the two ways to solve for F net? Give me one of them. Jasmine. F net equals m times a, right? We already have it up here. But what's the other way, Joshua? Sum of the forces in one direction. So then let's write out F net, let me erase this, sorry. F net in the x direction. Okay. Give me all the forces acting in the x direction. Amir, give me one. Friction. Do we want friction to be positive or negative? Negative. Okay. Plus, what's the other one? Sean? Fgx. Okay, so even though it's not on our little dot, it still acts in the x direction. And that's going to equal F net x. F net y. What's the forces in F net y? F normal. Is that positive or negative? Doesn't matter. Pick one. Positive. Okay, then what's the other one acting in the y direction? Fgy. And is that then going to be positive or negative? Negative, because we picked F normal to be positive. Okay, and that equals F net y. Questions on how you could solve for any of this? Okay, I didn't do it with numbers, but I think you guys get the idea. Okay, what's next?
In unit 1.
Any unit.
Yeah,
The types of forces.
The types of forces, and then I'll get to centripetal motion, Jasmine. Oh, sorry, Aranda. Okay, so then the types of forces. Force types.
elevator.
Elevator.
Alright.
Okay, so we'll do a problem in an elevator here in a minute, but let's continue on with types of forces. What else? Centripetal.
Can you give me a picture, please?
Okay, what else?
Um,
Dylan. Spring.
thank you.
Okay. What else?
I was not ready.
Kinetic force?
So we're naming types of the equations.
Oh no, I was just doing forces.
Never mind then.
Gravitation.
Gravitational.
Oh, my staple facts. Oh my god.
Okay, so then let's put our equations next to it.
There we go.
Do we have an equation for elevators that works?
No.
For every problem? No. Centripetal though is F sub c equals m a sub c. Spring is F x equals k times x. You remember there's that direction component that's a little bit confusing. Okay, but Fs equals k times x. What about gravitational? F sub g.
F times x. Acceleration with gravitation.
Good. And there's two gravitational equations.
Oh, that big one, G F1 F2 over.
I did?
Yes,
Yeah, it's a low
no,
dynamic.
it's still recording. It's still recording. Yes, it is.
Oh yeah, we're good. Okay. So F sub g equals g m1 m2 over r squared.
Okay, I have a question.
Yes.
Okay, so the radius is the radius. The radius is the radius plus the distance.
Good.
See the thingy?
Okay, so asking about the definition of r. So if this is my satellite. Well, here's my satellite.
Your satellite.
Right? It's a beautiful satellite. It's got all different kinds of probes coming off it.
It's an alien.
So if my satellite is 10 kilometers above the Earth's surface,
What's radius?
where is it from the center of the Earth?
You have to add.
Dylan. 10 kilometers plus r Earth. Okay, don't forget to add the r Earth because you measure from the center of the planet. Okay, good question, Jasmine. Thanks for bringing that up.
I was gonna ask something else and I forgot.
Okay. We want to try an elevator problem?
No. Not really.
Not really. Alright, so you're in an elevator. Here's your scale. Here's your person. Okay. The key with elevator problems is drawing that free body diagram. Okay, that's the key with these problems. So I don't want to draw it here because that's going to get complicated. Well, let's draw a little dot to represent my person.
Okay.
Okay. So then, which way do you want it to be accelerating? Up or down?
Up.
Up.
Down.
So it's accelerating up. So what does that mean about the direction of the net force?
It's also
It's
up.
down.
F net.
Oh, I lied.
It's up.
F net has to be up. So then, if I add two vectors, the sum of them have to be in what direction? Up.
I thought you said
Okay.
FN.
So what are my two vectors? What are my two vectors acting on the elevator? Gravity. In what direction does that go?
Can we go down?
Fg. And then
Netflix is up.
net force is up, but also what is the force acting on the person?
Normal force. is
Normal.
also Up.
Which one has to be bigger, gravity or normal?
Normal.
Normal, so I should probably draw this a little bit bigger.
With the fart.
Makes sense because it's accelerating.
Because it's accelerating upwards, exactly. Now,
I thought it was
an elevator problem isn't going to just ask which one's bigger, Fg or Fn. It's going to ask something about its apparent weight, or what does the scale read. Okay, so then what number does the scale read? Does it read the force of gravity, or does it read the normal?
normal.
It reads the normal, right? So that's the scale reading. Because the scale's pushing up on you. That's how it reads whatever you weigh. So if it's pushing up on you more than it normally does, are you going to weigh more? Weigh. Your apparent weight, is it going to be more or less?
Less.
If it pushes up more?
More.
More. My normal force is bigger. Okay? If I'm accelerating upwards, you feel heavier.
Oh, right. So you're heavier
Okay.
in an elevator.
You are not heavier, you feel heavier. Okay? Your mass does not change, and so your M times A doesn't change. So your force of gravity, your weight doesn't change, but your normal force does. Sean. Yep. Yeah, and if you're going over like big rolly hills in a car quickly, your stomach goes up and down too. Right, I guess there's not really a lot of hills around here, but
It belongs.
On the West Side Highway, it's this one bump that like, it feels like a roller coaster. Like if you go over fast enough, you will be up in the air.
There's a
Yeah.
video, right?
Okay, that's because you have a large normal force pushing you up, and it overcomes your gravitational force. Okay. What's next? We did elevators.
Wait, I have a quick question.
Yeah, Jasmine.
So F of n is on the table? Question mark?
Yes, it is.
Okay.
Fn, the normal force.
Yeah.
The normal force isn't on the table.
Okay, so
Let's talk about energy.
Energy. This class is over at 48, right?
I have no idea. Fill in check.
Yeah? Okay, thank you. So energy. What about energy?
potential energy.
Potential energy and kinetic. Okay.
Thermal or whatever that's called.
Work.
Thermal slash internal.
Yeah. And then there's
Spring.
work. Right?
Spring energy.
Spring energy.
But that's a type of potential, right?
It is a type of potential, but it's a different type of potential.
Okay.
That's spring. Gravitation.
And then you said work. Okay, so let's go through each of these.
You forgot
Potential energy.
gravitational.
Yeah, I'm gonna actually break up
Yeah.
potential energy into the two. So there's what's the first kind?
The gravitation.
Gravitational. Okay, and then there's also
Spring.
spring. Okay. So a problem I've noticed with some of you is that when I'm given a spring problem, sometimes you use the spring equation, which is what is it? ES,
What are we doing?
The spring.
spring energy.
Spring energy.
KX squared.
Yes.
Yeah,
that's
1/2 kx squared, but is it ES or is it PES? PES, thank you.
Oh.
Okay, so PES is 1/2 kx squared. If I ask the spring problem, be really careful if I'm asking for the force or the PES, the potential energy of the spring. Okay, because those definitely have different units. Okay, Jasmine.
So it was saying how much energy is stored in it, you use PS.
Yep.
And then regular spring is like what? If you push it, how much spring energy is?
Yeah.
Like,
What do you mean by regular
like what's
spring?
the instance of like not using PS and you just use KX?
So if you ask what's the weight on my spring, right? I put an unknown weight, it displaces it a certain amount with a certain K value. What's my unknown weight? Well, a weight is a force. So you want to solve for the force, not for the energy. Okay. All right. Thermal and internal. Is there an equation for that?
Is there?
No. When does it increase? When does the thermal energy increase? Friction.
Why not?
Okay, so that's heat that is lost and is non-recoverable. Okay, so once that energy goes into heat, you don't really get it back. You can't just magically heat something up and have it start like rolling up a hill. That's not how it works. Kinetic energy, 1/2 mv squared. Do we need to talk about that one much?
Not really.
Nah, it's pretty self-explanatory. Work. What is work?
Change in energy.
Delta E.
Oh my god.
Okay, and is it a vector?
No.
No.
It's energy.
It's a scalar. So it's also equal to force times displacement. But remember, it's not force times displacement, it's what's called a dot product. Force dot displacement, which takes away the vectors. You don't need to know that. You just need to know that when you do those two things together, the force dot the distance, it ends up with a scalar. Okay, so no matter which equation you use for work, you should end up with a scalar. Jasmine.
So if you're pushing something up a hill, right, and that's for the work, you do the distance of the hill or like the distance of like the
Let's finish this right up and then we'll do a problem. Okay? There's one more type of energy that we're forgetting about. Momentum's not an energy. What about mechanical energy?
Mechanical energy.
Mechanical.
That's funny, like, isn't that the total?
It is not the total.
No? Okay.
E total is the total energy. The mechanical is, Amir,
Is
your kinetic energy
plus
plus your potential energy. Good.
Any tech potential?
Yeah, because mechanical energy is defined as the energy that can do work. Okay, so can thermal energy do work?
No.
No. Okay, so you want all the things that can make your object move, or your object is already moving.
I was going to say.
Sorry, Amir. Okay, so that's mechanical energy, and it's different than the total energy. Units of energy. Joules, good. I do at the very end want to do an entire just like section on units. Okay, but Jasmine wanted to do an energy problem real quick. Yeah, so we'll do Jasmine's and then we'll do yours and then we'll do units, and I think.
They have diagrams.
Yeah, but that's not on the Regents. So it helps you, and we'll do that when we do Rose Melody's problem, but not for this one. So if I ask, and I give you a 5 Newton block. So the block weighs 5 newtons. What is that?
Force gravity.
The force of gravity. Okay, and I give you this distance, which is 2 meters, and I give you this distance, which is 5 meters, or 7 meters. Let's make it 7. Got too many 5s. And I want to know the work required. The work required is what? So then, how would I go about doing this? Joshua,
Can you use mass on gravity on height
which height?
or which height?
The 2. Okay, so the work required is just mass times gravity times the height. Okay, what's the same thing as the mass times the gravity? A Newton, that's its weight. So mass times gravity is already 5 newtons. And the height you said was 2.
10.
2 meters, so it's 10 what? Joules. Why can we not use the 7 in this equation? That's the distance, exactly. So if I wanted to use the equation force dot displacement, right? Work equals the force over displacement. Work equals, well, we went 7 meters, right? That's how far the block pushed. But what's wrong with that? It is the displacement.
You're not
But-
gonna have the same amount of force.
Expand on that. What do you mean we're not going to have the same amount of force? Same amount of force on what? The block. Okay, if I push a block across the level floor, it's not lifting its weight. Okay? What I'm doing is this is the force of gravity in the x direction. Do we know the force of gravity in the x direction? No, if I gave you an angle, then you could do it. But that's a lot of work. Right, you could solve for how much we're pushing it up and then times it by 7. That's fine. But you can't use this 5 newtons. Okay, good question, Jasmine. And then Rose Melody, I'm going to erase over here. You want to do one with the equaling the energies. Okay. So here I have a bridge. Here's my bridge. Beautiful. And I drop a ball. And here's my canyon. Okay. We want to find how deep that canyon is. Okay, so we want to find this height. What I give you is that the velocity final is 15 meters per second, and the mass is 2 kilograms. So what do I do?
Potential gravity.
Okay. Amir.
Can't you
Good. Okay, so that's what we're going to do. Let's do it out in our diagrams. Okay? Originally, when the ball's up here, what's its energies?
Potential.
Potential.
Potential, and that's it?
Yeah.
Okay? So we got, say, this much PE. Is this system going to lose any energy?
No.
No, so it's a big equal sign here. What's the energy at the end, at the bottom?
Kinetic.
Kinetic, all kinetic. Right? I didn't lose any energy, and I'm at the bottom, so there's no more potential. So now I have PE, G or S?
G.
G, it's gravitational, equals KE, S. Sorry, not KES, that's not a thing. Alright, so PEG is mass times gravity times height. Kinetic energy is 1/2 mv squared. Now if I want to solve for that, I can plug in my numbers, and all I need is h. Does that help, Rosemelody? Good. Jasmine.
Can't you just solve for K of E and know it's equal to P of G? Or solve for P of G and know it's equal to K of E?
So you can solve for them in equal, but I asked specifically for height. Okay, so I wasn't asking for the potential energy of gravity, I was asking for the height. And so then you'd have to divide. You'd have to do the height equals 1 over G would be V squared. 2, yeah, you would get that. If you divided by MGH, you would get height equals this. And so you couldn't just leave them as these two. You actually have to break them up into their component equations. Alright. Units time?
Yeah.
Units time. Can I erase this? Does everyone have this down, or should I erase everything else? Okay. No one complained, so. Units, the all-important units.
Oh my god.
Okay, so let's make a table. Okay, let's start with force. That's a really easy one. What are the units of a force? Any force.
Newton.
Newtons. Okay, which is what?
Oh no.
You break it down to its component, SI units. What is it, Sean?
Kilograms.
Kilograms times meters
Per second squared. Good. So the kilogram meter per second squared. And how do we get that? Oops. F
Another
equals
column.
M times A. There's going to be 4 columns. I really should have switched these two, but it's okay. So M is kilograms. A is meters per second squared.
Just switch it out.
Just switch it now? I'm switching it now. Okay, sorry about that. F equals M times A. And that gives me a kilogram times a meter per second squared. What's another unit?
Power, watts.
Power. That's a watt. Give me a power equation.
Mass times. Oh, that's momentum. Hold up. No, work over time.